Okay. Now, we do have a few announcements. Most of them you've heard before. A couple of them you haven't. Today is Wednesday the 18th. So let me get my slideshow set up. Wednesday the 18th. Today at 5 o'clock on the Birmingham West Campus in the Arthur Shores Fine Arts Building, which is also our gymnasium, our volleyball team will be taking on Southern Union in a match there. So if you can be over there at 5 o'clock, I can't. I'll be in class then, but they will be playing this afternoon at 5 o'clock. Tomorrow, they'll be playing Bevel State, but up in Fayette, Alabama. I'm not entirely sure where Fayette is, but somewhere up that way, Bevel State, and that will be a 6 p.m. game. And since we won't be meeting again, that's tomorrow, Thursday, Friday and Saturday, they're over in LaGrange, Georgia at the LaGrange College Tournament, and the times will be announced later. Okay, the next will be next week, so I won't worry with those now. And by the way, if you didn't know it or realize it, last year Lawson's volleyball team won more games than they ever had in the past. So it's a really good team. They're worth a look. So go support the team. The Scholars Bowl is currently recruiting players with knowledge in any subject, including history, literature, science, music, current events, mythology, and mathematics. Okay, so if you are either an expert at some fields or a master jack of all trades, but master of none, they can use you. So please consider meeting with them. Mr. Matthew West is the coach. His office is down this half flight of stairs here. The first classroom on your left is room 259. That's about halfway down the hall. The next one is 261. His office is in between 259 and 261. It doesn't have a number, but it's there in between those two classes. Now, the really good program they had on Monday for the Birmingham Holocaust Education Center, Darkness into Life, Alabama Holocaust Survivors Through Photography and Art. The exhibit is still on at the library on the Birmingham West Campus. It will be there through next Tuesday, I believe it is, September 23rd. The program they had was last Monday, so the program is through, but the exhibit will still be there through next Tuesday. So go by and take a look. It should be quite good. And the NASA Community College Aerospace Scholars Program will be accepting and evaluating applications through October 16th. It seems like a ways off, but I would highly recommend you go to some of these websites, find out what's involved. I believe Fred said it wasn't a very long application process, but he has participated in this. Ask him. He speaks very, very highly of it. Also, if you go down the hall here, about midway down the hall, on the left, there's a poster, and it features several of the other Lawson State students who have participated in the past years, and they all look like happy campers because I think they found it very, very beneficial program. Okay. Any questions on anything we've covered so far? All right. We are in Chapter 7, Applications of Integration. We have been all term. We're in 7.5, Work, and we're in Example 2, bottom of page 487. Now, if you don't happen to have a book, you can always go to larsoncalculus.com to see an interactive version of this type of an example. So here it is. A force of 30 newtons compresses a spring 0.3 of a meter from its natural length of 1.5 meters. Find the work done in compressing the spring an additional 0.3 meters. Okay? Now, variable force, obviously, right? Why do they give us two sets of pieces of information here? okay? They tell us force of 30 newtons compresses 3/10 of a meter from its natural length of 1.5 meters. And then it says find the work done in compressing the spring an additional 3/10 of a meter. Now, a lot of times problems like this are well worth pictures, okay? Pictures are worth hundreds, if not thousands of words, okay? So let's say we've got the spring here, and I'm going to draw a sort of fictitious spring here, very ugly fictitious spring. Original length of this meter, of this spring, is 1.5 meters. Natural length of 1.5 meters. Okay. Even if they're ugly pictures, they're worth it. Okay. What it says, you apply a force to compress the spring, and this force is 30 newtons. Okay. Compress the spring 0.3 meters. Okay, so I'm going to call that delta L, okay, for compression, length of 0.3 meters. When you applied that 30 newtons from the natural length of 1.5 meters. Then they say find the work done compressing an additional 0.3 meters. Not that first one. So we're really not interested in that. Why did they give us that piece of information then? Okay. If you are on the page and look toward the top of that page, you'll see the formula given that's called Hooke's Law. And this is what we're going to base most of the things on. And that tells you that force is equal to KD. Okay? Variable force, it depends on the displacement. Okay? Well, in this case, what I call delta L is what they're calling D. So maybe I shouldn't have called it delta L. I should have read the problem. Okay? They're calling it D. So what does this force, 30 newtons, is equal to K times 0.3 meters. I'm going to put my units in here. I didn't there, but I'm going to. What does this do for you? Anybody? What do you think we can get from that? The value of K, the spring constant. We can't work the problem if we don't know what the spring constant is. So this first bit of information allows you to calculate the spring constant. And what would that be? How would we get it? It's not that hard. Anybody? Divide both sides by 0.3 meters. Okay, this goes away, and that leaves us with a K of, if your easy way to do this is to move the decimal one place here, move that one place there, and 3 will go into 300 100 times. So it's 100 newtons per meter to have a unit with it. Okay? 100 newtons per meter. A pretty hefty spring. Okay? There can be springs much heftier than that, but that's a pretty hefty spring. All right, now that you've gotten that done, now you can go to answer the question. Find the work done in compressing the spring an additional 0.3 meters. Well, what we have here, now we're going to compress it from 0.3 to 0.6, right? This is a 0.3, there's a 0.6. If you go back another to the previous page, you'll see the formula there for work is what? I'll give you a hint. It's an integral from A to B. And what's your A in this case? 0.3 meters to 0.6 meters. You're finding the work done compressing that additional, so there's your A to B here. And what's your force? Now, they give it in terms of X. The upper things there in terms of D. I don't care what you call it. If you choose X, then we'll make this KX, but your K is 100. So you can pull that outside. 100, do you want X or D? Well, let's use X. What's the problem with D? Then our increment would be DD, which is sort of weird. Okay, so let's keep it X. So that would be X. This is now going to be X, not D. X dx. That was most of the problem. The calculus part, that's the easy part. Because you can do that, can't you? Be 100, it's antiderivative of X. Anybody? Second? X squared over 2, evaluated from 0.3 to 0.6. Okay? And what would that be? Okay, let's just get rid of the 2 and make this a 50 out here. So let's make this 50 times, and what you got here? What is 0.6 squared? Anybody? Not that hard. 0.36 minus 0.3 squared. Not 0.9. 0.09, right? Because 0.3 times 0.3 is 0.09. And Fred came in on that one. Okay. He saw we were in distress. He came to our rescue. Okay. Now, the rest of this is fairly simple, I hope. 50 times. What's the difference there? 0.27. And that times 50 would be... Second? 0.5. Is that what you said? Yeah, 13.5. Okay. And that would be in what units? I was carrying my units around, but then I lost them. This is in Newton per meter, but then this was in X squared. That would be meter squared. So that 1 meter cancels out the one of the meters. The meter in the denominator cancels out one of those. So this would be in Newton meters. And what is a Newton meter? A joule. Very good. 13.5 joules. And that's what they got to. Good for them. All right. Good deal. Any questions on those? All right. Let's see how they did it, to see if they did it any differently. It can't be too much different, but let's see what they did. By Hooke's law, the force F of X required to compress the spring X units from its natural length is F of X is equal to Kx. That's what we got from the top of the page. Okay? Because F of 0.03, they gave us this, was equal to 30. The force was 30 newtons required to compress 0.3 of a meter. That told us that our spring constant was 100 newtons per meter. Okay, they didn't give us the units, but they are newtons per meter. So we use that. F of X is now 100x. Okay, that's the force applied, applied force. To find the increment of work, assume that the force required to compress the spring over a small increment delta x is nearly constant. Okay, so the increment of work is delta W, which is force times the distance increment, which would be 100x delta x. Yeah, we just went to the formula because I'd already done this before, but this is how you get to it. And then you, because the spring is compressed from 0.3 to 0.6 meters, less from its natural length, that's a weird way to say it, the work required is W is equal to the integral, as you said before, a to b of f of x dx that we got from this thing up here, okay? And our a was 0.3 meters, b was 0.6 meters, the f of x was 100x, and the delta x became a dx. And that gave, when you do what you do, they kept the 100 inside, I'm not sure why, but the x would be x squared over 2, so that made it 50x squared, which is exactly what we had, only we had the 50 on the outside. Evaluate that from 0.3 to 0.6, and that gave you, okay, they did it that way, 18 minus 4.5. I'm not sure I would have done it that way, but it is correct. That's 13.5 joules. Newton meters, which is joules. Note that you do not integrate from 0 to 0.6 because you're asked to determine the work done in compressing an additional 0.3 meter, not the entire 0.6 meters. Okay, so read the problem carefully. That's what that's saying. The summation of increments, okay, let's see. No, they're skipping example 3. So let's go back. I think this will be probably our best shot at white space. Oh, the swimmer returns. Okay. Dawson's here. Okay. Is Josh on the way?
No, he can't make it today.
Oh, okay. All right. We're just finished doing example 2 in chapter 7, applications of integration, 7.5 work. We just finished example 2, but you can also find that at larsoncalculus.com, an interactive version of that type of example. We're just getting ready to do example 3. It's not on the slide set, so I went back to find a slide with white space from example 2. A space module weighs 15 metric tons on the surface of the Earth. Okay? What is a weight, by the way? Weight is the same as a force. So some books call it F sub W, meaning the weight, the force associated with weight. That's not completely standard, but some books say that. Okay, so that's 15, and so this is 15 metric tons. Now this is poorly written. I'm sorry. This is written by a mathematician, not by a physicist, because that's not quite how you should express this. Number one, a metric ton. An English ton measures weight. That's why I was going from. A metric ton does not. Does anyone know what a metric ton is?
2,200 pounds.
Okay, very good. That's what the weight of a metric ton is. But what a metric ton is 1 megagram. It's 1,000 kilograms. Okay, that's what they call a metric ton, and that is 2,200, equivalent to 2,200 pounds of force, weight. So this is actually a mass. It's not a weight. Okay, and 15 metric tons would be 15 times 10 to the 6 kilograms. Okay, Now, I don't know if we need that here. I think perhaps we do. Let's just see. Let's read the whole problem. Okay. How much work is done in propelling the module to a height of 800 miles above the Earth, as shown in the figure there? Please look at your own figure. Does everybody have a book or something you can see the figure on? It's figure 749. If not, I'll try to draw it, but far better to look at theirs. 800 meters above the Earth is shown in that figure, 749. It says use 4,000 miles. So yeah, you're right. They're using miles. Metric tons is a SI unit, basically. Miles is a U.S. customary, so they're really screwing up the units here. 400 miles is the radius of the Earth. Do not consider the effect of air resistance or the weight of the propellant. Two big things you're ignoring. Because the weight of the body varies inversely as the square of the distance from the center of the Earth, the force, F of x, exerted by gravity is C. Weird way to do this. C divided by x squared, okay, where C is a constant of proportionality. Because the module weighs 15 metric tons on the surface of the Earth, and the radius of the Earth is approximately 4,000 miles, you can then come up with, as a physicist, this makes me scream, okay, because they're mixing up units like crazy. But as long as you stay within those units, no, this is incredibly messy. Okay. All right. I had forgotten this problem was this messed up. Okay. So what we want is how much work is done in propelling the module from a height to a height of 8,000 miles above the Earth, considering that it was initially at 4,000 miles from the center of the Earth, so you're going to really 4,800 miles from the center of the Earth. So that's the first thing to keep in mind. You're going from 4,000 miles, that's on the surface of the Earth, to 4,800 miles up in space. Okay, so that's the first thing to note in this problem. Okay, now the second thing to note is the weight varies inversely as the square of the distance from the center of the Earth. So that's what they tell you. F of x is, it's a varying inversely, so that'd be 1k over x squared, but they're using c rather than k, where k is a proportionality constant. Okay? Now, just like in the last problem, this is on the surface. Okay? So, on the surface, this is 15 metric tons, which is not a U.S. customary measure, so you should not be quite doing it this way, but as long as you keep it in metric tons, it'll be okay. So I don't even know, I'm going to have to write out metric tons, because we're not using it in megagrams, okay? So let's just write it as metric tons is equal to C over 4,000, because that's where you are on the surface, 4,000 miles squared. Okay, So that would be 16 square miles. Okay. Multiply that by 15, and hopefully you get what they got, 240. 240 million. You get that? 15 times 16? Let's see, 15 times 4 would be 60. And you have 4 sets of 4, so that'd be 240. Yeah, so 240 million. So C is equal to 240 million. Okay. Notice they don't use your units, but the units would be metric tons dash miles squared, square miles. That's multiplied by square miles. They're not messing around with units. Sort of wise is the way they're handling the units. Okay. So what's the increment of work? Okay. This is how they like to approach it. The increment of work would then be the force, which are going to be, that makes f of x to be 240 million, and I'm tired of writing all these zeros, but I will, over x squared, which actually, I know I'm not going to want to integrate that. So let's write this as 240 million. How would we write it? X to the, I don't like to integrate dividing things, x to the minus 2. That's the f as a function of x. Okay? All I've done is rewrite this as x to the minus 2. Get out of there. So, that's your force. Your increment of work would be that force times your dx. So that would be 240 million. I'm tired of writing these zeros. X to the minus 2 dx. Delta x. Since they're doing a delta here, let's do a delta there. Okay, delta x. Okay. Then what would be your integral? W would be 240 million, I'm tired of writing all these zeros, times the integral of x to the minus 2 dx. And where are we going from? Yeah, from the 4,000 to the 4,800. Seems like we're going to have some big numbers in this problem. What you think? Okay, so let's see what we've got. Tired of writing all those zeros. 240 million times what? Entire derivative of x to the minus 2.
It's just x.
Second?
It's just x, right?
Not quite. X to the, add 1 to minus 2. Second? Negative 1. And then you divide by the negative 1, so it gives you a minus 1 over x. Now I'm going back to that just because I think it's easier to evaluate. You see that? And that's going to be evaluated between 4,000 and 4,800. Okay. Okay. I wish I had more room on the board. Let's carry it up here and do it. I'm tired of writing all these zeros. 240 million times a minus 1 over 4,800 minus a minus, which is plus 1 over 4,000. Okay? Now, how you want to proceed with this is up to you, kind of, okay? Frankly, I think I'd find it easier to distribute the 240 million across both of those so I don't have to find least common denominators. I think things will go into it. So let's see, if we wipe out these two and those two, then 48 will go into 24.5 times, right? So that would be 5, 0, 0, 0, 0. So that's going to be, if I'm doing my math right, minus 50,000. Then we got a plus, and we do 4,000 into that. So the 3 zeros will wipe out 3 zeros there. And 4 will go into this, 6, 0, 0, 0, 0, plus 60,000. Are you following what I'm doing? It's a weird way to do this, but it's a lot easier than the least common denominators. So this comes out to be 10,000. Now, here is where I go a little nuts with them. Oh, no, they got it right. Their distance was in miles, and the force was in, what they called the force was in metric tons. Okay. Mile metric tons. Okay. And then from somewhere, they picked up, and it's reasonable, what the miles was, how many feet that is, 5,280 feet, and a metric ton, as Patrick was saying, was about 2,200 pounds. They actually used 2,205 pounds. Now, weird to wait till now to do it, and that would give you an answer in foot-pounds. And then they turn around and get it to joules. I think it would have driven a physicist crazy to do the problem quite in this backhanded manner, but that's what they did. Do any of you want to see how they did those conversions? They just write the numbers down without showing you. Do you need to see that or not? You don't care, okay? Anyone want to see it? It's up to you. You don't take their word for it. Yeah? Okay. It's fine. It's just a conversion issue. And then they also use a conversion factor that 1 foot-pound is 1.35582 joules, which is another weird conversion. Then the work would be in joules. So my question is, why didn't they give you this in kilograms, have you convert that to newtons, give the radii and the distance not in miles but in kilometers or meters, and then you worked everything in that, and you wouldn't have to have so many conversions at the end of the problem to do. But it's up to you. Okay. By them just showing you the answers, you don't see how much is involved in getting to those answers. So it seems like an easy way to do it unless you were actually doing all your conversions. So, but if you don't want to see those, that's fine. So the work done, they came up with something in the order of, trying to remember, 10 to the 3rd joules would be kilojoules, to the 6th joules would be megajoules, to the 9th would be what's the next one? Goodness, my brain's going dead on me here. Giga, okay, gigajoules. And so this would be 116.4, no, I'm sorry, 157.8 gigajoules. Okay, if you didn't want to do scientific notation. That's an incredibly large amount of work. Don't think I want to do that this afternoon. All right. Any questions? No one desires to see how they got from this answer in metric ton, or was it? Metric ton, mile metric tons, looks like a really simple answer, into gigajoules, or 10 to the 11th joules. All right, if not, we'll move on to this. Summation of the increments in the form of your delta W can either be done like we've been doing, your force times your distance increment, which is F dx, okay? Or, if it works better for you, a force increment times the distance. And that's delta F times x. The second interpretation of work is useful in problems dealing with the movement of non-rigid substances such as fluids, chains, rope, line, those kinds of things, that it's easier to measure incremental distance, incremental amounts of your weight times a given distance. And usually that's the force you're dealing with. And that's what they're getting at here, which leads to example 4. Emptying a tank of oil, okay? A spherical tank of radius 8 feet is half full of oil that weighs 50 pounds per cubic foot. Find the work required to pump all of the oil out through a hole at the top of the tank. Please show the picture. Oh, thank you so much. Okay. So it starts off being exactly half filled with oil. Okay. Now you might say, who in the world has spherical tanks anyway? Have you ever seen a spherical tank? Have you ever driven down I-65 past Clanton, Alabama, and seen their water tower? Clanton, Chilton County, what's that famous for? Peaches. What's that water tower? You've never noticed it. It's a big peach, which is really just a spherical tank with a leaf on it, or something. They painted it to look like a peach. Yeah, you've seen spherical tanks. Oh, you should have. Okay. Pay attention next time you're out. Get off your cell phones. Okay. All right. Consider the oil to be subdivided into discs of thickness delta Y. Okay. That's what they're showing here. Here, okay, little increments of delta Y of radius X, okay. Now, that disk is radius X, and boy, this is hard to see on here, isn't it? It looks like there's a line here somewhere, but I sure don't, that doesn't make a lot of sense. Oh, here. I guess it's, yeah, there's your X. So if you projected this up into this disc that you have here, the radius out to there would be X. They got it there, weird location, as shown in this figure. Okay? Now, a real key here is where you put your origin. And it appears to me, since they have the x-axis down here, the origin is at the South Pole, the very bottom point of that sphere. Okay? And the y-axis going up there. So therefore, if it's a radius of 8 feet pumping a disc at a time of this oil out through the top. This is how you think of it. Now the disc, if your delta Y is small enough, is all going to have the same distance to travel, right? That disc, if the delta Y is thin enough, has the same distance to travel. Well, if your origin down here, then your distance to that disc is Y, and the amount that you're going to be pumping is 16 minus Y. Does that make sense? It's the distance you pump this disc of oil to get it to the hole. Okay, 16 minus Y. Okay. Now, delta Y, that's going to be your delta in the problem here. Now, what we've got to figure out is what the weight of that oil is. Okay? They told you the oil weighs 50 pounds per cubic foot. Okay? Now, how many cubic feet, so to speak, are in this disc of oil? Well, what's the volume of that disc of oil? The area of the disc, which is area of that disc, it's a circle, right? Area of a circle, pi r squared. I always thought pi were round, but no pi r squared. No, okay. So that's your circle. Your radius there is your x. So it's pi x squared, okay, times the thickness, the delta Y. Okay, now we got sort of a little problem here. We got x's in there and y's in there. So at some point we're going to have to get it in terms of one or the other. Probably in terms of y. So if you got y's here, you need to get that x in terms of y. So how are we going to do that? So that's what we've got for our disk. So pi x squared delta y, and we're going to pump it 16 minus y feet. Okay? So the force, remember, is 50 pounds per cubic foot. So if your delta y is in feet and your x is in feet, and the picture isn't good here, because they showed this, they make it seem like that's 8 feet. 8 feet is to the edge here. Your x here is somewhere inside the 8 feet. So don't think the x is 8. It's not. The x is something inside of 8. Now what we've got to do is figure out that x in terms of y. This is your y here. Okay? If you go from the center here, let's do a triangle that goes from the center here, that's an 8, down to the center here, which is 8 minus y, out to here. But from here, we know that from the center to any point out here is going to be y. Center to any point on the edge of the sphere, 8 feet. So that's going to be 8. The hypotenuse here is 8. This is going to be 8 minus y, and this is going to be our x. And I think from that, let's see. All right, let's do that again. From here to there is 8 feet. From here to the center of the disk is 8 minus y. And this is your x. Okay? So Pythagorean theorem tells us the x is equal to the square root of 64, that's 8 squared, minus 8 minus y squared. Buy that or not? That gets your x in terms of y. So let's do the math there. This will be 64 minus, and what's 8 minus y squared? Remember how to do that? Square the first, 64, twice the product of the two, minus 16y plus y squared. Buy that? Okay. Now when you do that, you'll see the 64's go out. And then the minus of minus, this will be the square root of 16y minus y squared. Because the minus outside changes both of those signs. Okay. So that's what your x is. Fortunately, what do we do with that x? Square it. Okay. So as we were saying before, the mass of that is, the volume of that is going to be pi x squared. So we get pi times 16y minus y squared, because when you square a square root, you just lose that, times dy, the thickness of that, multiply, that's the volume of the oil, multiply it by 50, that's 50 pounds per cubic foot, and we just got that in terms of cubic feet. And then then we multiply that by how high we pump it. And what is that? 16 minus y. Is that right? That's how high you pump. This is the mass of that disc. No, the weight of that disc times the height of the disc, and that's going to be how much work you do. Force times the distance is height is work. So let's get this in a little bit neater form. The 50 and the pi can come out front, okay, right? The integral, and where are you going from? What are your y's going from here? That first disc that you pump out is going to be from
0.
All right, you're doing the one at the bottom then?
Isn't it 0 to 8?
Okay, that's what I was going to say. You're going from the bottom. You're going to pump that bottom one out first. You can do it that way. 0 to 8, okay? I think I would have done, well, no, it's not going, no. Okay. Yeah, that's right. If you do the bottom first and then do every layer, that's okay. All right. Now, what goes next? Got the 50 pi out. Notice here, this factors into 6y times 16 minus y. So you have a y times 16 minus y squared, don't you? I don't know if that's helpful or not, but you do have that. And then you have your dy. Now, I don't think that's all that helpful now that I look at it. Because really, I think the best way to do this is to multiply those together. So what is this thing? 16 squared. 256, is that right? Help me, somebody. I think it's 256 minus 32y, is that right? Times, or plus y squared, and then multiply it by y. You get y here, squared there, and a cube there. And that's what you're integrating from 0 to 8 dy. Now what is the antiderivative of that? Help me, somebody. See, setting this thing up is the hard part of the problem. Really, the integral is not that bad. The calculus is not that bad. Or I want to say that. What is the answer? Antiderivative of 256y. Okay. And half of 256 is 128. 128y squared minus, no help here, 32y cubed over 3 plus y fourth over 4, evaluated from 0 to 8. All right. I'm going to let someone with a calculator do those. I'm not going to try to do those in my head. Be 64 times 128 minus, whoa, I'm going to let you do that one. 32 times 8 cubed divided by 3 plus 64 squared divided by 4. I should be able to do that one, but I'm not. I'll let you do it. And what do you get? Oh, the 10 o'clock scholar.
11.
Oh, 11 o'clock scholar, sorry. Okay. Okay, what, tag team? Okay. Look, when you come, the women leave. Is that the story of your life, huh? Huh? No, she had an appointment today. Okay. But I could have passed that up, but I didn't want to. Okay. All right. We've done everything the way the book did, so I assume they got the same answer. What did you get? Anybody?
3,754.67.
And then multiply that by 50 pi. Please tell me you didn't delete it before I said that. Okay, good.
589,781. Run it up to 82.
Ah, okay, 82 foot-pounds. All right. Now, what they did is estimate to see if that answer makes sense, which is a pretty good thing to do. A hemisphere would be 1/2 of the sphere. The volume of the sphere is 4/3 pi r cubed. Your r is 8 here, so you can do that math too. You need a calculator for that almost as much as this one. And multiply it by its density, and then estimate raising that 8 feet. Now that's not a good estimate, because if you raise this 8 feet, you'd only get it this much. You only get the top part of that you're doing. You still got to get the rest of it out of there, but at least it gives you a general idea of how much. And that came out 428,932 foot-pounds. So it would be something greater than that, and the 589,000 makes sense. That was just an estimate, which is not a very great estimate, but just an estimate. So I'll let you decide whether that was worth it or not. Okay. That was example. Oh wait, let's see how they did it. Okay. So let's carry on. Because you have an increment of force, each disk is given by its weight. The delta F is then your weight of the disk. And and the weight would be 50 pounds per cubic feet times the volume. Well, the volume of that disk would be pi r squared, but the r is now your x, times your delta y, which is exactly what we did, okay? But the problem here is you got delta y, but you got x squared in there. Well, that's a problem. For a circle of radius 8 and center at 0, 8, you have x squared plus y minus 8 squared is equal to 8 squared. That's, I believe, exactly what we had for our Pythagorean theorem, thing that we did. Very similar to it, okay? And we came out exactly this, x squared is equal to 16y minus y squared. Well, they didn't even mess with doing x. They did x squared, which is smart because the next thing you're going to do is square it, which is already squared up there. So you just plug that in. Well, your delta F is the 50 times that. They just repeated that line up here, and then they're going to take this in for your x squared. Okay? Okay? And note that the disk, so that's just your delta F, the incremental force, weight, okay? You're going to lift that incremental weight 16 minus y feet, okay, as I showed here. This increment you have here is 16 minus y. And lift that up. And that then gives you the work done is your delta F, which they have on the previous slide, times this. And that's your 50 pi times 16 y minus y squared, okay? Remember, that was back here, 16y minus y squared. Delta y times the 16 minus y. They wrote it almost the same way I did. And then they just magically came up with that is 50 times 256y minus 32y squared plus y cubed delta y. They didn't show you how they did that. My guess, they foiled these two, and that would give you the same thing. I just thought it was easier to square this one and then multiply by y. But they didn't show you all the agony of foiling that, but it wasn't that bad, okay? So that's your increment of work. You integrate that from your 0 to 8, just like Patrick said. That first increment down there, and then every increment above that up to 8. And that would be 50 pi, which I pulled outside, times 256y minus 32y squared plus y cubed. And that was 50 pi, finally they pulled it outside, times that, which we evaluated. And I guess you did it, because I didn't. That to be 589,782 foot-pounds. Now, again, this is a mathematician, not a physicist. If you remember our original problem, we only had, I'm just going to go back real quickly here, radius of 8 feet, 50 pounds per cubic foot. Those are the only two numbers given. Basically one significant digit. They didn't do 8.00 feet or 50.0 pounds, one significant digit. Okay, now that's a lot to ask, but really what you would say here at the end, if this was truly a physics problem, about 600,000 foot-pounds. Because you don't have significance to give you 6 digits here that makes sense. So really what you say, about 600,000 foot-pounds. But that's a physics issue, yes. I'm sorry? I can't hear you. we don't do significant. Mathematicians usually don't deal with significant digits. Only physicists worry about that, so you don't have to worry about it here. No. All right. Or in Cal 3 either, if that's what you're asking. I can't hear. So to estimate the reasonableness of this result, and here they show it, then they do 1/2 the volume times the density. The volume is 4/3 pi cubed, where r is 8, and half of that would be 2/3 pi times 8 cubed. 950, that would be cubic feet times pounds per cubic feet. That gives you that many pounds. So lifting the entire half tank of oil 8 feet doesn't get it to the top, but it just gets it up there. That would be the work of, if you just elevated that up, that would be 428,932 foot-pounds, and then you still got to pump all that out, so that would be another little bit. Seems reasonable that the work done would be significantly more than that, but not a huge amount more. Okay. They think it's significant. All right. Now, they're leaving off lifting a chain, which is not one of my favorite pastimes, so I'm almost not inclined to lift the chain, but let's do it. A 20-foot chain weighing 5 pounds per foot is lying coiled on the ground. How much work is required to raise one end of the chain to a height of 20 feet, which is the entire length, so that it's fully extended as shown in the figure? And they didn't show the figure. Hopefully you've got books to look at the figure. All right. So we have a total length of 20 feet. Okay. We've got a incremental, you got sort of a density type thing of, let's just call it rho y, to be 5 pounds per foot. 5 pounds per foot. Now that is a weight unit, not like a couple problems ago when they had a mass unit in there. Okay. So how much work is required to raise one end of the chain to a height of 20 feet so that it's fully extended? Okay. Now, what you're doing, you're lifting incremental lengths here. But it's also, in some senses, an incremental force as well. Okay? What, the rho sub y? Was that it?
I was just trying to read kind of what you were.
Okay.
I didn't know what was next to the 20.
The what?
I couldn't read what was next to the 20. That's all.
Okay. I just sort of made up the terms there. Okay. So, if you have an incremental length, that's going to be, and you're raising it up, we're going to call that our delta y. Okay? Now, the force, the weight of that delta y is this, 5 delta y, because it's 5 pounds per foot, and delta y is measured in feet, so your weight would be 5 delta y. Okay? Now, your work then, the delta W, the incremental work of raising that, these incremental lengths, you're lifting it when you really need a picture. I really was trying to resist drawing a picture. this incremental length here, you're going to lift y units up for whatever. The y is a variable, and the y is going from where? The amount that you lift is your y. So this will be 5 y delta y. Okay, y is how far you lifted that incremental piece, and you're going to be lifting that y units. Okay, now y is your variable, so what you have is the total work is equal to 5 times the integral, and where are you lifting? From dy here. What's the minimum y? 0 to 20. Y dy. Okay? And I think that's all she wrote. Okay? And what is that? 5 times antiderivative. Again, here, definitely, the calculus is the easy part. What's this? Y squared over 2. Is that what you said? Okay, y squared over 2 evaluated from 0 to 20. So that would be 5. Okay, yeah. Let's take the 5 halves out. 5 halves. And I'll write 5/5. I don't know where that came from. 5 halves out front. And then you'll have 20 squared is, anybody know? 400, right? And 2 will go into that 200, and this will be 1,000. And what's your units? Foot pounds. Okay. And that's what we got. Okay. A relatively easy problem to do. I've sort of drawn a picture. It made a little more sense, but it's pretty straightforward. Once you figure out the deltas, delta work, delta force, delta width, the length, whatever you're going to do your delta in, then it works out pretty easily. The next example, you'll consider a piston of radius r in a cylindrical casing. It's shown in the figure. Hopefully you all got the figures, I hope, right? As the gas in the cylinder expands, the piston moves and work is done. If P represents the pressure of the gas, so it's all right to go on and eliminate this one. Okay, this is one long section. Okay, so P is the pressure in the gas. Okay, now what is pressure? Anyone know? Force per unit area. Now, easy way to remember that for me anyway, and maybe y'all don't think in these terms. Have you ever checked the pressure of the air in your tires?
Yep.
Okay, what did you measure that in? PSI. What does that stand for?
Pressure surface interface?
Second.
I don't know,
What does PSI stand for?
per square inch.
Pounds per square inch. Pounds is a measure of force. Square inch is a measure of area. That's what pressure is. Pounds per square inch, Newton per square meter, whatever it is, force per unit area. So that's what pressure is. Okay. So, piston move. If P is the pressure of the gas in pounds per square foot, they gave you the units here. Pounds per square foot. So this is different units in pounds per square inch, but I remember pressure from that. Okay. Against the piston head, V represents the volume of the gas in cubic feet. Okay, V is volume. Okay, and that's in cubic feet. Okay, and of course what volume is, if it's a cylinder, what's the volume of a cylinder? Assume it's a second. Pi r squared is the area. It's something else. The length, the height. Pi r squared h. Now the h is going to be our incremental part. That's what we're going to be increasing by a little bit. Because the radius is fixed, that's not going to change. So the change here is going to be your this. So the volume of the gas is pi r squared h, but the h is going to be our incremental part. Okay. Where are we here? Okay. V is volume of gas. Then the work increment involved in moving the piston delta x feet. The delta x is going to be our h. Not h, but delta x. Okay? Now, work is, the delta w is going to be in force, okay, times your delta x. Okay. Well, this is an area here. This is a volume. If you multiply a volume times an area, you get the length, right? I'm sorry, did I say that wrong? Divide the volume by the area, you get length. Okay? Is that right? Volume divided by an area gives you the length. Okay? So this should be your pi r squared delta x divided by your pressure. Is that right? No. Sorry, did it wrong. Pressure times, because your area is per, okay. Duh. This is the pressure, that's a little p, times the volume, and pressure is force times delta V, I'm going to call it, and this will be the pressure times your pi r squared delta x, okay? Because this is force per unit area, and the area will wipe out that area, so basically that's your f of x dx, okay? But we don't know the force. In fact, we don't even know what we're, okay. We're only given pressure and volume. So basically, this is our work increment that we've got, P delta V. So as the volume of the gas expands from V1 to V2, the work done in moving the piston is equal to the pressure, which is a constant we're assuming. I think so, yeah, that's not variable, times your integral from V1 to V2 of your dV, okay? Now, no, the pressure is not constant. It's variable also. Assuming the pressure of the gas is inversely proportional to the volume. Now, where do you get that? The pressure of the gas inversely proportional to the volume. Anyone ever hear of, goodness gracious, what's the guy's name? I'm going blank on his name. But the pressure times volume is constant, okay? Because at constant temperature. Now that's another thing we're going to ignore, changes of temperature here, because we're not telling how the gas is expanding. It's probably from an explosion. But if it were at constant temperature, the pressure times the volume is constant. That's Boyle. That's what it is, Boyle's law. Okay, Boyle's law. So they're getting all sorts of things in here. So pressure times volume is equal to a constant. This is Boyle's law. I'm pretty sure it is. Okay, so therefore the pressure is equal to some constant over the volume. So that's what we put in here then. Whatever that constant is, integral from V1 to V2 of 1 over V dV. Okay. That's the work done by an expanding gas in any kind of a cylinder. It didn't have to be right circular, but we're choosing that. So let's do example 6 then. You'll have to remember this because I've got to erase it to do example 6. Okay? A quantity of gas with an initial volume of 1 cubic foot, so V1 is equal to 1 cubic foot. Okay? And a pressure of 500 pounds, so P1 is equal to 500 pounds per square foot, pounds per foot squared. Okay? Expands to a volume of 2 cubic feet. V2 is equal to 2 cubic feet. Find the work done by the gas. Assume the pressure is inversely proportional to the volume. Okay. So, if P1V1, Boyle's law, is equal to a constant, and this is 1 cubic foot times 500 pounds per cubic foot, per square foot, okay? Pressure is force per unit area. This would be a constant of 500 foot-pounds. Yeah. Okay. Interesting. That is a work unit right there. They aren't keeping up with that. They just say 500. But it is foot-pounds. So, what we have then is the work done is the constant, which is 500 foot-pounds, times the integral from V1, which is 1 cubic foot, to V2, which is 2 cubic feet, of dV over V. Wasn't that what the last slide was? That was our final discussion there, okay? Now this is sort of making sense because if you notice the units here are cubic feet per cubic foot. No units, dimensions. So that's why your work is, the units are all out here, okay? Now, what's the antiderivative of that? Antiderivative of 1 over V dV. Oh, it's been a while, hasn't it? Antiderivative of 1 over V dV. Help me, somebody. Natural log of V. Okay, evaluated from 1 to 2. So this would be 500 foot-pounds times what? Anybody? Hey, it's not that hard. Just write it down. Log 2 minus log 1. What's log 1? 0. So there's your answer. And now you can use your calculator to do 500 times log 2.
346.
Second? 346.
346.57.
Let's do it 347 foot-pounds. In fact, I'd argue about 350 because nothing you have has more than one significant digit, so I'm being generous by giving 2 significant digits there. They did 346.6 foot-pounds. Okay. Good deal. Now, they put absolute values by the V, which maybe I should have 2, but the thing is, V can't be negative here. It's going from 1 to 2, so that's not necessary in this problem. Okay. That finally finished 7.5. Homework exercises here would include 5 or 7. They're both at Calc Chat. 7's at Calc View. Any of the odds 9 through 13, they're all at Calc Chat. 11's at Calc View. Any of the odds 15 through, wow, 15 to 25. They should all be at Calc Chat. Okay? Then do 27. It should be at Calc Chat. 29 or 31. They're both at Calc Chat. 29's at Calc View. 33 should be at Calc Chat. 35, you can think about doing that as an exploring thing, so it should have the answer at Calc Chat. If not, don't sweat it. Any of the odds 37 through 41, they should all be at Calc Chat. Then Boyle's Law, hey, I remembered it right, was 43. That should be at Calc Chat and Calc View. And then hydraulic presses, which use some of those concepts, 47 or 45, 45 or 47, they should both be at Calc Chat. There's modeling data at 49, and you can certainly, that should be at Calc Chat as well. There's a section project, the Pyramid of Khufu, which is also the Great Pyramid of Giza, I guess it is. Oldest of the 7 wonders of the ancient world, and you can play around with that if you'd like. Any questions? 7.5. How are we doing with time? We've got a little left, don't we? Not much. Okay. Let's move on to 7.6. Okay. All right. Let's go from current slide. All right. If you didn't notice it, we just did. Both of these were in the last section we just did. All right. But that's neither here nor there. We're still in Chapter 7, Application of Integration. 7.6 is moments, center of mass, and centroids. Are most of you pre-engineers? Yay or nay? Yes? Ryan, you yes? Pre-engineer? Yeah. How about Devin?
Computer science.
You what?
Computer science.
Which science?
Computer.
Computer science, okay. And have you changed again, or you're still math? Okay. What are you thinking of going into? Electrical engineer, so you're basically pre-engineer. Dr. Briggs talked you into that, didn't he? Okay, I thought so. Okay, he was noted for doing that. All right, but 7.6, I'm sure math majors are going to run into this, so I know, Patrick, are you still a math major? Yeah, okay. But the pre-engineers almost certainly are going to be dealing with moments, center of mass, centroids. You do this in statics and dynamics, it's going to be all over the place. So that's one reason we do it. objectives here is first understand the definition of mass. Okay? That's not from a physics viewpoint, but from a calculus viewpoint. Find the center of mass in a one-dimensional system. Find the center of mass in a two-dimensional system. Find the center of mass in a planar lamina. Okay? That's getting towards something else. And use the theorem of Pappus to find the volume of a solid of revolution, which is really an easy thing. It sounds like it might be hard, but it really is easy. So let's first talk about mass. Several important applications of integration are related to mass. Mass is a measure of the body's resistance to changes in motion. And you physicists want to tell me what that is also called? Resistance to changes in motion. Inertia. Okay, that is a short way. Mass is a measure of a body's inertia. It's resistance to changes in motion. Okay? If I were to throw you really hard a ping pong ball, how much effort would it take for you to stop that ping pong ball? Not very much. Okay? Even Ryan can do it.
About the same amount traveling.
Yeah. And the thing is, probably the air resistance will knock it down before it gets to you anyway. Not much. But if I threw you just as hard a bowling ball, how much effort is it going to take you to stop it? Now you're probably going to jump out of the way, right? Okay, yeah, I thought so. Okay, a lot more. Why? Because the ping pong ball has very little mass, very little resistance to change of motion, whereas a bowling ball, very massive, is going to take a lot of force to create, to change its motion. The mass is independent of the particular gravitational system in which the body is located. That means your mass here on Earth is the same as your mass on the moon, is the same as your mass if you were any other place else in the solar system or in the universe. Your mass doesn't change as long as you're the same size. Your weight changes big time, okay? In fact, if you want a really good weight loss plan, go to the moon. You've just lost a sixth. You're down to 1/6 of the weight you were before. Unfortunately, you haven't lost any mass, so if you come back to Earth, you've just gained it all back again. But that's beside the point. However, because so many applications involving mass occur on Earth's surface, the object's mass is sometimes equated with its weight, which they did in an earlier problem that drove me crazy. Okay, this is not technically correct, and yet you did it. Okay, weight is a type of a force, and as such is dependent on the gravitational field in which you're located. The fact that we're all located within the same gravitational field anywhere on the surface of the Earth, we can use them as if they're interchangeable. They're really not. Force and mass are related by this equation. Force is equal to mass times the acceleration of that gravitational field. But since this is a constant everywhere on the surface of the Earth and as far above and below the surface of the Earth as you'll ever get, we can count it as if these are equivalent because they differ only by a constant. Okay, which is the same for any conversion factor as well. Okay, in the table below, I can't believe they do this much here in the math book, lists some of the commonly used measures of mass and force together with their conversion factors. Now they say commonly used mass. How many of you ever used slugs as a unit of mass? Did you even know it was a unit of mass? Okay, it is. But no one ever used it. The measure of force in the U.S. customary system, we only deal with force. We don't deal with mass. The only way you get a mass is to take the weight, the pounds, divide it by your acceleration due to gravity, and that's how many slugs it is. No one measures how many slugs you got. In the SI system, they just call it international, but SI system, kilogram is a measure of mass, and a Newton is a measure of force, and a Newton is a kilogram meter per second squared. Just like the relation is up there, so one uses slugs. In the CGS system, which is the smaller cousin to the SI system, and this used to be called MKS, for meter kilogram second. This is centimeter gram second. Smaller units. The unit of mass is gram the dyne is the gram centimeter per second squared. Now, for what it's worth, a pound is considerably more than a newton. Almost 4.5 newtons. 1 pound is 4.5 newtons. Okay? A slug is about 14 and a half, a little bit more than 14 and a half kilograms. For what it's worth, no one ever uses slugs. A newton, on the other hand, to a reciprocal of that, is about between a fifth and a quarter of a pound. Okay? So it's a smaller unit. A kilogram by the way, a slug is a very significant amount of mass. About 14 and a half, more than 14 and a half kilograms. So a kilogram is a significant amount of mass. Okay? So a kilogram is a very small fraction of a slug, about 7/100 of a slug. A dyne, on the other hand, is an incredibly small unit. That would be an incredibly small number of pounds. A gram is a very, very small increment of a slug. A dyne is exactly 10 to the minus 5 newtons, and a foot is pretty close to 3/10 of a meter. I don't know why they're giving you all these, just to give you a general idea. So meters are big measurements, feet are smaller measurements. Slugs are huge measurements of mass. Newtons, pounds is a fairly good size unit of force. A newton, considerably less. Dynes, incredibly small. So, find the mass in slug of an object whose weight at sea level is 1 pound. Okay? So what is its mass? I can't believe they're asking you this, not in a math book, but we'll do it.
It's 1141.
Is it? Well, this is going to be really easy. Oh, 41. We've just gone over it. We'll start with example 1 next time then. Sorry about that. I was thinking we ended at 45, but it's 40. Okay. Now, not enough to do any additional homework exercises there, but we'll move from there. Now, 7.6, a reasonably length section, but I think we'll be able to get through it a little bit faster than we did 7.5. Hopefully we will. Let's end this.